This lecture video will cover reaction quotient and equilibrium constant. Okay, please read the OER textbook chapter section 13.2 for more detail. For dynamic equilibrium, there are two terms that help us determine whether the reaction is already at the equilibrium already or not. Okay, so the first one is the reaction quotient. Reaction quotient is going to tell you about the status of the reaction. Okay, so it's going to help you to predict whether the reaction would proceed to the forward reaction or the reverse direction, or it's already at equilibrium. So the second term is equilibrium constant. Okay, so we are going to use uppercase K in this case, as the name implies. Okay, so this is the constant. Okay, so it's going to stay constant. Equilibrium constant is going to tell us exactly what happened at equilibrium, right? Which species is predominant, right? Whether it's going to be product or reactant. So that's what the equilibrium constant is going to be able to tell us. Okay, so note that this uppercase K is not equal to the lowercase k that we learned in chapter 12. Okay, lowercase k indicate this one is the rate constant. It tells us about how fast the reaction go. Okay, this one is the equilibrium constant. Okay, it tells us about how far the reaction goes. Now let's take a look at the mathematical expression of these two terms. So that way you understand these two terms a little bit better. So I'm going to use the generic equation of A plus B going to C plus D, and this is the reversible reaction. Okay, so in order to express the reaction quotient Q, what you are going to do is that you are going to express it with the concentration of the product over the concentration of the reactant. But note that all the coefficients have to be the exponent. Okay, so you are going to raise the concentration of each of the product with its coefficient. Okay, so for example, in this case, C, right? You are going to use concentration of C, and it's going to be raised to the power of its coefficient. Okay, so same thing if you have D. Okay, so you are going to multiply all the concentration of the product, okay, divide by the concentration of the reactant, and you are doing the same thing with their coefficients as well. Okay, so this is how you express the reaction quotient. This reaction quotient here, if you're looking at, is kind of like tell you about the ratio, right? So it's the ratio between the product and the reactant, right? So if you're looking at how to express the equilibrium constant, you are going to express the same thing as Q. Okay, so K is going to be expressed identical to Q. Now you might ask me, well, Q and K expressed with the same mathematical expression. So what are the difference between these two then? Well, just note that Q is going to be at any time during the reaction. Okay, but K, remember the name is equilibrium constant. So therefore it's going to have to be at equilibrium. Okay, so it's going to be only at equilibrium. If you calculate Q, right, and if the value of Q come out to be equal to K, we can conclude that at that time or at that point of reaction or this condition of the reaction is already at equilibrium. That's what we can tell you. Okay, so when Q is not equal to K, we can see that at this moment or at this condition of the reaction has not reached equilibrium yet. That's what we can tell. Okay, so that's the difference between Q and K. So now you might ask me about the unit. Okay, so the Q and the K unit are going to be no unit. Okay, so it's going to be unitless. Okay, so the reason for that is because of this concentration, even though it's raised to a certain power, but this concentration here are going to be referenced based on 1 molar. So for example, before you plug in all of these, right, so this concentration is going to be based off 1 molar. So you already cancel those units, right? So therefore, in this case, the concentration that placed in here has no unit. Okay, so that means Q and K come out unitless. Okay, not the same as small k, right? If you go back to the rate constant unit, this is chapter 12. Okay, so this is chapter 12. The unit of this is going to be based off reaction order. Okay, so they are not the same. Okay, so these are not the same. Okay, so all right, so let's take a look at an example. Okay, so these are examples that you are going to be given on the exam as well, and also you're going to see on the homework as well. Okay, so you are going to give equation, and you are going to ask to write the expression for either reaction quotient or equilibrium constant. Okay, so let's take a look at one. Okay, so example 1, in order to write out a reaction quotient, we are going to start with Q, right? So it's going to equal to product. Okay, so it's going to be concentration of ammonia, right? So raised to its coefficient, so it's going to be square. Divide by concentration of nitrogen, right? Multiply by concentration of hydrogen cube, right? Because of that coefficient. Okay, so let's take a few minutes here. Okay, so let's complete B. Okay, so do the same thing with K as well. Can you do example 2 as well? Okay, so let's pause the video now and complete this and check your answer when you're ready. All right, let's check your answer together. So answer for B would be Q equal to product square, right? Divided by reactant, right? Concentration. Now, example 2. So this one is asking you to find out equilibrium constant expression. So that means this one is going to be the K, not the Q. Okay, so Q is the reaction quotient. K is equilibrium constant. Okay, so this one would be K equal to the product, right? So we have two products here, right? So it's going to be concentration of carbon dioxide raised to 8, right? So and then water raised to 10 divided by reactant, right? Raised to their coefficient. Okay, and then for B, the K would be equal to product over reactant again. Okay, so don't forget to raise to those coefficients. Okay, so the next thing, we are going to tie this back into calculation now. Okay, so let's take a look at a reversible reaction between carbon monoxide and hydrogen gas that produce methanol. Okay, so this one is tell us that equilibrium mixture into liter vessel. Okay, so found to be this many mole, blah blah, right? And then it asks us to calculate the constant. Note that K subscript C, this C refer as you are expressing equilibrium constant in terms of concentration. Okay, so this small c tell us that you are going to have to express it in terms of concentration. So that means if you want to find out Kc, right, we know that according to the expression that we learned, you are going to use product over reactant, right? So again, don't forget the coefficient as the power. Okay, so that means in this case, we need to find out the concentration. Okay, so you can't just put in the mole. Okay, so you need to find out the concentration at equilibrium. So remember, the reason why it's not Q is because this is said equilibrium mixture is already at equilibrium. Okay, and also it tells us that you need to find out Kc. So that means this is going to be the concentration at equilibrium. Okay, so it tells us that there are several moles that involved with this, right? So in order to find concentration or molar concentration, right? So this bracket is the concentration. You are going to use mole over liter. Okay, so that's going to be the concentration of methanol. Do the same thing for carbon monoxide, right? So you're going to get this many mole per liter. Okay, and then the last one would be hydrogen gas. Okay, so the next thing after you get all of this is just to plug all of this value back into the Kc expression. Okay, so if you do that, you are going to get Kc come out equal to 104.7. Okay, so now let's check sig figs, right? So we have 3 sig figs here, 3 sig figs here, 3 sig figs. So your final answer have to come out with 3 sig figs. So the final answer would be 105. So later on in this video, you are going to take a look at the significance of the value of the K. Okay, so for now, I'm just going to leave this as it is. Okay, so we're going to revisit this about the value of the Kc later. Okay, so let's take a look at the next example. Okay, so the next example is asking to find out the equilibrium constant again, right? What is equilibrium constant, right? K. But now this one is subscript P. What does subscript P mean? Okay, so the K subscript P is going to be the equilibrium constant that is going to be expressing in terms of partial pressure. Okay, so that means in this case, it's going to involve with gas. Okay, so Kp is going to be involved with gas. It's going to use partial pressure instead of the concentration. Okay, so in this case, what we are going to do, right? So your expression is still going to be the same with Kp, but instead of using the concentration, you are going to use partial pressure now. Okay, so it's still going to be the same, right? Partial pressure of the product, right? So raise that pressure to its coefficient, right? So this is 2, right? You are going to divide this by the partial pressure of the reactant. Okay, so same thing, it's still going to be product over reactant still. Okay, but we are going to use partial pressure instead of concentration. Okay, so now in order to calculate this, we would need to find out partial pressure of each of these species. Okay, so the problem gives us the total pressure. Okay, it also gives us the partial pressure of the product, right? So that's what we know. So that means we know this, but we don't know this yet. So that means we cannot plug it into the expression of Kp yet. So that means we need to first find out partial pressure of each species at equilibrium first. Okay, so in this case, we know that the total pressure at equilibrium, okay, so it's this much. So that means it's going to come from the summation of everything that within the reaction, right? So that means it's going to come from those reactant and product add together. So that means if you subtract the partial pressure of what we know, right? From the total pressure, you are going to get the partial pressure of the reactant. Okay, so in this case, partial pressure of the reactant will come out equal to 0.34 atm. Okay, so once you know partial pressure of the reactant, we already know partial pressure of the product. So all you need to do is just plug them in. Okay, so don't forget to square that, okay, because of the coefficient again. So you are going to get Kp come out equal to 0.5956. Okay, so this is two sig fig. Therefore, your final answer is going to contain two significant figure. Okay, so 0.6. So again, we are going to talk about the significance of the value of the K later in this lecture video. Okay, so now let's relate Q and K together. Okay, so I'm going to use another reaction now. So this reaction is going to be the combination reaction between sulfur dioxide, okay, and oxygen that produce sulfur trioxide gas. Okay, so the Q, okay, so it's going to be reaction quotient. Okay, so it's going to be expressed as product over reactant still. Okay, so what I'm going to do is that I'm going to explain the graph. Okay, so if you plot this graph, okay, so what you are going to do is that if you start from the reactant, okay, so you are going to observe that the concentration of the reactant, right, is going to start at a high concentration. Okay, the reaction of the product will start at the low concentration. Okay, eventually, once these achieve the equilibrium, you are going to observe that the concentration of each of these species are going to remain constant regardless of the time progress, right? So as time progress, the concentration doesn't change, right? So that's when we know that equilibrium already achieved. So now I'm going to tie this graph back into the Q and K value. Okay, so the graph that we are going to take a look at next is going to be reaction quotient, which is going to come from this expression here, plot against time. So now let's take a look at this with me. Okay, so at time zero, okay, so what does it mean? Okay, so at time zero, if you think about this, these are at time zero, right? So if you think about this at time zero, we have zero concentration of the product. This product right here, the concentration is equal to zero concentration. So therefore, in this case, 0 divided by anything is going to equal to 0, right? So therefore, in this case, the value of this graph is going to start at 0 because of that, right? Because Q at this point is equal to 0 because we have no product at this point. Okay, so as the time progresses, you are going to see that you are going to have more and more of the numerator. You are going to have less and less of the denominator because the reactant, right, is going to decrease over time, but the product is going to increase over time. Therefore, you are going to end up with increasing value of the Q, right? So therefore, you are going to observe this value of Q increasing as time progresses, right? And it's going to increase up until a certain point. Eventually, all of these concentrations are going to remain constant. Therefore, the ratio between the product and the reactant are going to remain constant, right? So the ratio between these two are going to remain constant. So therefore, you are going to observe that the Q value is going to remain constant. So that's why you see on this graph right here, the value of Q doesn't change at all, right? So this is going to indicate that the equilibrium already reached, right? So that means this one is going to indicate that this is the point where Q value is equal to K. Okay, so that's why we call equilibrium constant, because it's constant, right? It's remain the same. It doesn't change as the time progresses. The reason for that is because at this point, again, the concentration of each of those species remain constant. It doesn't change. So therefore, it's making the ratio stay constant. Because this reaction is reversible, as we can achieve equilibrium starting from reactant, we can also achieve equilibrium starting from product as well. Okay, so in this case, this graph right here represents equilibrium that is achieved by starting from product. Now let's take a look at this graph together. Okay, so at the beginning of this graph, we are going to give the high concentration of the product, right? Because we want to start at the product. Okay, we are going to give a 0 concentration of the reactant in this case. So now the reactant would be concentration of 0. As the time progresses, you are going to see that the species that has higher amount, they are going to decrease, right? Because in this case, this is going to end up converting to the reactant, right? So you are going to observe that its concentration would decrease and more of this would be produced. So that's why you are observing their concentration to increase. Eventually, it's going to reach equilibrium when these species concentration are no longer changed. Okay, so that's when we know that the equilibrium already achieved. So now if you plot the graph between reaction quotient versus time, so similar to this graph right here, what you are going to observe is that, think about this with me, okay? So since Q is equal to the high concentration of this product, right? So you have a very high concentration of the product, okay? So a big value. but you are divided by 0, right? Because you are you're starting with 0 concentration of the reactant in this case, right? So this concentration equal to 0. Anything divided by 0, right? You are going to get the infinity value. So that's why this graph, you are going to start with the infinity, right? So, and as this point, right? So as you start to see this, right? So as more and more of the reactant is being made, right? So you are going to have higher and higher of the denominator. You are going to have less and less of numerator. You are going to see that the Q value is going to decrease over time up until it's achieved equilibrium where these concentrations are no longer changed, they stay constant. So therefore you are going to have a constant value of Q, and that constant value of Q is going to equal to K, right? So this is when Q equal to K is indicated. This constant value right here is the equilibrium constant, is already at equilibrium point. Okay, so the conclusion of this graph is that when you are looking at K and Q, okay, so before the equilibrium achieved, Q is going to be at any value, okay, so and Q would be equal to K when the equilibrium is reached, okay, so when the concentration is no longer changed, and you can achieve the equilibrium from either reactant or product, okay, so you can achieve equilibrium from either direction. Please note also that at constant temperature, the K value is also going to be constant as well. Okay, so this is similar to the rate constant, small k as well. Okay, so the rate constant is never changed unless you change the temperature. Okay, so this K is the same thing. All right, the next thing we're going to take a look at is I'm going to look at the driving force that causing the reaction to achieve equilibrium. Okay, so I'm going to show you the graph that plot between energy and the concentration. Okay, so the concentration is going to be the concentration between the reactant and the product. Okay, so in this case, when you have Q that is not equal to K, so let's say that when Q is less than K, is not at equilibrium yet. Okay, so Q less than K, what does it mean? Okay, so this means if you think about Q, right? So Q, when you do the expression, is always product over reactant. So that means when Q less than K, the less value or the small value indicated at this point, you are going to have high concentration of the reactant, which means you have high concentration of the denominator, right? So which is going to cause the value of Q to be small. So at this point, it's not equilibrium yet. At this point, you have high concentration of the reactant. At high concentration of the reactant, you are going to observe that the energy at this point is going to be high, as will indicate that this state right here is not stable. Okay, so which means that in order to make this state to stable, the energy is going to decrease. Okay, so it's going to decrease by reducing the concentration of the reactant. So that means the concentration of product is going to increase, right? So as the concentration of the product increase and the concentration of the reactant decrease, it's going to cause the Q value to increase, right? So as the Q value increase, eventually it's going to reach the point of the equilibrium when Q equal to K. When Q equal to K is indicate that this already at equilibrium, and at equilibrium, the energy is at the lowest. Okay, so it's at the stable state. Okay, so that's why I want to actually shift forward, right, to produce more of the product in order to reach that equilibrium point at the lowest energy. Okay, so now same thing, if you start the condition where you start off with high concentration of the product, right? When Q is greater than K, this is not at equilibrium yet. This is indicate that at this point, you have more of the product than the reactant, right? So since you have more of the product, in this case, you are going to end up with high value of numerator, higher than the denominator. So you are going to end up with a big value of Q, right? So at this point, again, it's indicated you have high concentration of the product. Since the concentration of product is high, the energy at this point is also going to be high as well. Okay, so it's not stable. So in order to make this stable, the reaction is going to shift, right? So that means the reaction is going to proceed in the reverse direction to produce more of the reactant. As the reaction proceeds in the reverse direction, right, you are going to end up with more and more of the denominator, right, less and less of the numerator. Therefore, eventually the value of the Q is going to dig to the equilibrium point where the energy is at the lowest. So the take-home message of this is that when Q are less or greater than K, those conditions are not at equilibrium yet. And the reaction is going to proceed one way or the other in order to achieve this lowest energy point, which is at equilibrium when Q value is equal to K. The next thing we are going to take a look at is we are going to take a look at the importance of Q. Okay, so Q, or reaction quotient, is used to predict direction of change. Okay, so as we know, right, Q is going to indicate at any point of the reaction or at any time of the reaction, right? But K is at equilibrium. So therefore, when you are going to predict whether the reaction would proceed forward or reverse, you are going to compare Q with K. Okay, so what does it mean? Okay, so when Q equal to K, is already indicate that that reaction or at that point of the reaction is already at equilibrium. Okay, so it tells us that the forward and reverse are going to proceed in equal rate. Okay, so when Q are not equal to K, that's when you are going to be able to find out which way it's going to shift, right? Which way the reaction is going to proceed to. Okay, so when Q greater than K, as I mentioned before, right? So when you are looking at Q, you are looking at between the ratio between product over reactant. When Q have a greater value than K, is indicate that at this point of the reaction, you have more of the product, right? Because you have more of the numerator than the denominator. So you are going to end up with a big value, right? So that means in this case, when Q greater than K, we can say that at this point is not at equilibrium. You are at this point, you have more of the product than the reactant. Okay, so since the reaction is not at equilibrium yet, you have more concentration of the product than the equilibrium. Therefore, in this case, the product are going to convert to the reactant, right? So that means in this case, the reaction would proceed toward the reactant, right? In order to produce more of the reactant in order to reach equilibrium. Okay, so similar to this graph right here that I mentioned earlier, right? So when Q greater than K, okay, so it's going to reduce the amount of product by converting to make more of the reactant, right? Until it's going to reach equilibrium again, right? So that's what it means here. So it's going to proceed toward the reactant in order to reach that equilibrium point. Okay. Now when Q less than K, so this is going to be the opposite scenario, right? So when Q less than K is indicate that you have less of the product, and at this point you have more of the reactant, right? Because you have higher value of the denominator than the numerator, so you are going to end up with a small value. So in this case, it tells us that this point is not at equilibrium yet. Okay, so at this point you have more of the reactant than the product. Okay, so just make sure that you correct that sign right there. So you have more of the reactant than the product at this point. Okay, so what does it mean then? Well, it means that the reaction would shift toward the product, right? Because it's going to end up making more product in order to achieve the equilibrium. So the take-home message of this is that Q can be used to tell us whether the reaction is already at equilibrium or not, right? So when Q equal to K is already at equilibrium, but when they are not equal to each other, that's when you can use Q to predict whether the reaction would proceed toward the product or toward reactant, depending on the concentration that you start with. All right, let's take a look at examples so that way you understand a little bit better. So this reaction right here, I'm going to color each of these species. Okay, so we know the constant value of Kc. Okay, so we know that this is at constant temperature. The reason why it's giving you a constant temperature because the K value can change, right? If you change temperature. So this value is based off this temperature. That's what it tells us. Okay, so I'm going to color code each of these species. That way it's easier for us to understand. Now let's take a look at the graph. Okay, so the graph is plot between the concentration and different mixture. Okay, so I'm going to show you two graphs. Okay, so this is before reaction and after it's reached equilibrium. Okay, so the graph plot the same thing, okay, concentration and different mixture. Okay, so again, this is before reaction, this is already at equilibrium. Okay, so let's take a look at it. Okay, so let's say mixture one, before reaction, I'm going to start with only the reactant, right? So I'm going to start only with these two species, right? So those two species has that color. Okay, so this is before reaction, we start with those two. Remember, again, when you're looking at Q, right? Q equal to product over reactant. Since at the beginning, right, you don't have any product at all, so product would be zero. So 0 divided by anything would equal to 0. So therefore, you are going to observe that the Q value equal to 0 because of that. Okay. Over time, the amount of these, right, is going to convert to amount of the product. So therefore, it's going to this color of blue and red are going to eventually is going to reduce, right? It's going to be less and less of blue and red, and there will be more and more of the green and yellow. So as you see, once it's reached at equilibrium, like you are going to see less amount of the reactant and more amount of the product. Okay, so at this point, you are going to observe that the K value is going to equal to Q and is going to equal to this value right here. Okay, so At this point, I want you to just ignore this value just for now. Okay, so just know that eventually, right? Since you start with the pure reactant, eventually at the end you are going to get the mixture of both reactant and product mixed in this mixture. As you learned previously, that the equilibrium can be achieved from both directions. So that means we can also achieve equilibrium from starting with just the product as well. Okay, so the mixture two, this mixture here contain only the product, right? So only the product. So as you see, like the reason why the value of Q is infinity, because Q is the ratio between the product over reactant. So in this case, you don't have any reactant at all. So reactant would be zero. So anything divided by zero is going to be infinity, right? So that's therefore the value of Q would be infinity at this point. Okay, so, and again, as the time proceeds, right, the amount of the product is going to reduce, right, to increase more of the reactant in order to achieve the equilibrium. So therefore, when you're looking at mixture two at equilibrium, right, you are going to see less of the concentration of the product, right, in comparison to the before the reaction start, right, and you are going to see more and more of the reactant that's being produced. Okay, so eventually it's going to achieve the equilibrium where the Q and K value are the same. Again, as I mentioned before, right, equilibrium can be achieved by either direction, okay, by either start from pure reactant or pure product. So now you might ask me, can we mix them all together? Can equilibrium be achieved just from mixing all together? The answer is yes, right? So if you mix all together, reactant and product mix all together, eventually it's going to reach equilibrium point as well. Okay, so it doesn't matter which one you start. If it's reversible reaction, eventually the equilibrium would be reached. Okay, so, and note that the K value, whether you start with pure reactant or pure product or mixture of all of those, right, you are going to notice that the K's constant will remain constant, right? They all are going to be the same. Okay, so you probably notice as well, it doesn't matter what are the concentration, right? So as long as the ratio of those are the same, okay, so the K value would come out the same. So that means in this case, K is constant, K will never change as long as the temperature constant. Now let's take a look at example one. Okay, so this reaction is between hydrogen gas and bromine gas. Okay, so to produce hydrogen bromide gas. Okay, so, and this picture right here represent the reaction at equilibrium. Okay, so it tells us that at equilibrium, let's say like this picture represent mole of each of those gas, right? So if you count the number of mole of these, you are going to get 9 mole of HBr. Okay, you are having 1 mole of hydrogen. Okay, so you have 1 mole of bromine. Okay, so that's what we have. Okay, so we are going to use this information here to help us to answer example one. Okay, so let's take a look at example 1A. Okay, so write equilibrium constant expression. So this one is going to be the same as we learned before, right? It's going to be the ratio between product over reactant. Now to determine the value of equilibrium constant, so this one you will need to find out the concentration of each of those first. So pretty much you are going to use mole, right, divide by liter. So this is divided by 1 liter. So after you do that, you are going to get Kc equal to 9 squared over 1 over 1. Okay, so you're going to get 81 for Kc value. Okay, so if you're looking at this picture right here, you can see that at this equilibrium point, the species that has highest concentration would be HBr, right? Is HBr, right? Is the product. So in this case, HBr would have the highest concentration, which makes sense if you think about this. Kc, okay, so it tells us the ratio, right, between the product over reactant. So that means if the product and the reactant at equilibrium, they come out to be about the same. So if these two come out to be the same, they are going to be able to cancel out. So that means the K value probably going to come out closer to 1, right? So that means whenever that you see K equal to 1, it tells you that the concentration of product and reactant are about the same, right? But in this case, the K value is not equal to 1, it's a lot higher than 1, right? So when Kc a lot higher than 1, it indicates that the numerator is going to be a lot bigger than the denominator, right? So if you have a big numerator and you have small denominator, you are going to get a big value that's greater than 1. So that's what this means, right? So that means in this case, what does it mean then? Well, as Kc a lot greater than 1, you are going to see that this is already at equilibrium, right? Because that's what the K tell us. Okay, so K tell us that it's already at equilibrium. Okay, but at this equilibrium, you are going to see that you are going to end up with more of the product than the reactant. So we can say that at this point, at this equilibrium, the product is favored. Okay, so product is favored or product predominant at this point. So now we are going to use the previous calculation to help us to determine the different condition. Okay, so now if you looking at different condition, okay, so this one is tell us that to decide whether this condition is already at equilibrium or not. Okay, so remember, in order to find out whether the reaction is going to be at equilibrium or not at equilibrium, you are going to use Q, right? Because Q would tell us if Q come out equal to K, the reaction is already at equilibrium. But if Q come out greater or less than K, it's not at equilibrium, and we can determine the direction whether it's going to proceed to the reactant or the product, right? According to the relative value of Q and K. Okay, so let's take a look at A. Okay, so in order to find out Q for condition A, same thing, right? You are going to use product over reactant. Okay, so you're going to get Q. In this case, Q come out to be less than K. What does it mean? Q value that come out less than K value indicate that at this point, you have more of the product. It's not at equilibrium yet. You have more of the product at this point, right? So because why? Well, if you think about this, right, Q equal to product over reactant. If the Q value is small, that means you are going to have big value of the denominator, right? So that means in this case, you have more of the reactant. Therefore, in order to achieve equilibrium, the reason why we need to achieve equilibrium is because at equilibrium point, right, the energy is at the lowest, is the most stable state. So therefore, in this case, you are going to need to shift the reaction toward the product. The reaction is going to shift to the right side, right, toward the product. Okay, so to make more of the product in order to achieve the equilibrium point. That's what it means. Okay, now let's go ahead, complete B and C. Okay, and then let's check your answer with me once you're done. All right, let's check your answer with me. Okay, so B, do the same thing. You are going to calculate for Q value. Q come out to be 81. So this one is indicated Q and K are equal to each other. So that means condition B is already at equilibrium. There is no shifting. Okay, so the rate forward, the rate reverse are equal. Okay, so that means it's already at equilibrium. Okay, so at equilibrium point, you are going to see that you are going to have more of the product than the reactant, because at this point, as we mentioned before, right, the product is favored. Okay, but there is no shifting. Okay, all right, C. Okay, so C, Q would come out equal to 122. Well, in this case, you have Q greater than K. Okay, so that means at this point is not at equilibrium yet. You have more of the product than the reactant. Therefore, in this case, the reaction is going to shift toward the reactant. Okay, so make more of the reactant to achieve an equilibrium point. Now you already see the importance of the reaction quotient Q, right? It tells us the direction of the reaction, right? So whether it's gonna shift toward the product or shift toward the reactant, or it's already at equilibrium, right? So here we are going to take a look at the importance of the equilibrium constant K. Okay, so the equilibrium constant K will tell us how far the reaction proceeds, right? So at equilibrium, how far the reaction proceed, right? So for example, whether it's going to have more of the product at the equilibrium or it's going to have more of the reactant at equilibrium, and why one species is favored over the other at equilibrium. So that's what we're going to take a look at. Okay, so note that when we talk about equilibrium constant K, we are looking at equilibrium, which means that the rate forward is going to equal to the rate reverse. And we know that the equilibrium has been achieved when the concentration of the product and reactant remain constant, right? But as I mentioned in the previous slide, right, those concentration are not necessarily have to be equal to each other, right? So one can be greater than the other, but as long as their concentration remain constant, that point is already indicated that is the equilibrium point. Okay, so let's take a look at the first scenario. Okay, so first scenario, when you have a reactant convert to product. So in this case, we are going to consider when the K value is greater than 1. Okay, so when the K value is a lot greater, okay, so this is a lot greater than 1, what does it mean, right? So again, when we are looking at the equilibrium constant similar to Q, right? So we are looking at the concentration of the product over the concentration of the reactant, right? So is the ratio between those two. Again, the reason why Q and K are different is because Q can be at any point of the reaction, but K have to be at equilibrium. Okay, so that means at equilibrium, when K is greater than 1, is indicate that at equilibrium, you are going to observe more of the product than the reactant, right? Because if you think about this, right, if you have a big numerator, you have small denominator, you are going to end up with a big or a large value greater than 1, right? So what does it mean then? Okay, so in this case, if you plot a graph, okay, so energy diagram, so the reaction coordinate diagram, right, against the reaction coordinate, okay, so what does it mean then? Well, it means that if you compare the stability between reactant and the product, you are going to observe more of the product at equilibrium because the product is having lower energy than the reactant, right? So the product are more stable, therefore the reaction would proceed to a more stable state. So in this case, it's going to produce more of the product. So that means in this case, the reaction once is proceed, right? So once it's reached the equilibrium, you are going to observe the concentration of the product greater than the concentration of the reactant. So that means the K value can also tell us as well about the stability of the product versus the reactant. Okay. Now, if you think about this, right? So if you, again, looking at the concentration, right? So eventually you are going to see that eventually once product is being produced, right? So before it's 0, right? So for the reactant, before it has a high concentration, reactant would decrease over time, product would increase over time, and eventually once it's reached equilibrium, these two concentrations are going to remain constant, right? Will no longer change. But as you see, right, the concentration of product would be higher than of the reactant. Okay, so that indicates that the product are more stable. Okay, so then if you're looking at the second scenario where the value of K is a lot less than 1, for example, like 0.00 something, right? So the K value is very small. Small K value indicate that at this point, at this equilibrium point, you are going to observe more of the reactant than the product. It means that this reaction doesn't proceed far toward the product. So that's why you have more amount of reactant left in the flask, right? So if you think about in terms of reaction coordinate diagram, it tells us that the stability of the reactant is actually more stable than the product. Therefore, the reactant that is already stable, it doesn't want to convert to product. So that's why you are going to end up with more concentration of the reactant than the product at the equilibrium. Okay, so if you plot the graph, what you are going to observe that the concentration of the reactant would definitely decrease, right? But it's going to decrease by not much, right, until it remains constant, and eventually product will also being produced as well, right? So until it remains constant, and you will see that at constant period or at the dynamic equilibrium period, you are going to see that the concentration of the reactant would be greater than of the product. Okay. So again, that is indicate that the reactant are more stable than products. Okay, what does it mean when K equal to 1 then? Okay, so when K is equal to 1, we can say that the stability between the reactant and the product are about the same. So that means at equilibrium, the concentration of these two are going to be similar, right? Going to be the same. So in this case, you are going to observe that at equilibrium, these two going to come out to be about the same. Okay. So the reason for that is because these two have equal stability. All right, now let's take a look at example. Okay, so this would be the conceptual problem. Okay, so 1 to 5 here. So let's take a look at 1. Okay, so we are going to consider this reaction A convert to B and C. Okay, so it's giving us a certain value of the equilibrium constant. Okay, it asks us which species have the highest concentration at equilibrium. So according to what we see earlier, right? So small value of K, right? So this is to -9. So this is very small, it's a lot smaller than 1. It tells us that a lot or majority of the species that present in the reaction mixture still going to be A, right? So the highest concentration would be A, right? Because it indicates that it doesn't convert much to B and C at all, right? If you think about in terms of product over reactant, right? You have a lot of A, right? You have a big A and you have a small amount of product, right? So that's why your K value come out to be a very, very small value. So that means this one is indicate that this reaction has highest concentration of A. It also tell you that this reaction here, A is more stable than B and C. That's why it doesn't want to proceed toward the product, right? So it doesn't want to convert more to the product. Okay. All right, now let's take a look at 2. Okay, so it's asking us that with given information here, okay, so is this reaction would be slow or quick? or is there not enough information to answer? Okay, so note that this K, okay, so this is the equilibrium constant. Okay, equilibrium constant only tell you the relative amount of the product and the reactant. It doesn't tell us anything about the rate. Okay, the only thing that tell you about the rate would be the small k. Okay, so small k is the rate constant. So that means this problem, we don't have enough information to answer. The reason for that is because the big K, right? This is the thermodynamic function that tells us only about the stability between reactant and the product. It doesn't tell us about the speed. But if you want to know about the speed, then you need to looking at the kinetics function, which is the rate constant. Okay. All right, let's take a look at 3. Okay, so 3. K and Q. Okay, so you are having two value. It asks which of the following statement is true, right? So in this case, as you see, the K and the Q are not equal to each other. So that means at this point, it indicates that this given condition is not at equilibrium yet. Okay, so that means in this case, the one that are false would be A and E. So I can eliminate those. The reason for that is because it's not at equilibrium yet, because Q and K are not equal to each other. So now between B, C, and D, with what else we can eliminate? Okay, so remember Q value tell us about the direction of the reaction, right? Because it's not at equilibrium, so it's gonna shift one way or the other in order to reach equilibrium. It's either going to shift to the right or it's either gonna shift to the left, right, in order to reach the equilibrium. So in this case, we can eliminate B, right? So that's not true, right? So something gonna happen, right? So it's gonna shift one way or the other. So now the next thing we're gonna take a look at is you can see that the Q value is less than K. What does it mean? When Q value less than K, if you think about this, right? So Q is going to be the ratio between product and reactant. When you observe small Q value that is less than K, that means at this point, you have more of the reactant than the product. Right? So if you think about this, right, you have small numerator, you have a big denominator, therefore the value would come out to be smaller value. So that means in this case, at this condition right here, is not at equilibrium. So it's going to shift, and it's going to shift in order to minimize the amount of reactant that it has, right? So that means it's going to reduce the amount of the reactant and it's going to produce more of the product. So it's going to shift from reactant toward the product. So that means in this case, it's going to go forward, right? It's going to favor the forward direction. So that means in this case, the answer would be C, right? So it's not at equilibrium yet, and the reaction will progress further toward the product, okay, or shift to the right. Now let's take a look at 4. Okay, so this reaction here is given as the K value. Okay, so again, this is the uppercase K, so it's the equilibrium constant, asking us which one has the highest chemical potential energy. Remember, high energy is going to associate with the least stable, right? So as you learned in chapter 8 before, right, when we talk about stability versus energy, right? High energy mean less stable. So in this case, asking us which one would have less stable. So we talked about this before, right? K is the thermodynamic function that tells us about stability. So that means if you think about this, the more that is produced, right? Whatever species that is favored at the equilibrium, that species is going to be the most stable, right? So in this case, if you think about the K value come out in 100 range, it's a lot greater than 1. When K a lot greater than 1, what does it mean? Okay, so if you think about this, right? So K equal to P, which is product over reactant, right? When K is greater than 1, it means that at equilibrium, you have a lot of product than the reactant at equilibrium. Okay, so that means the reaction would not shift anymore. It's already at equilibrium. So that means in this case, it's indicate that because remember the equilibrium is already at the lowest energy, right? If you think about the Q, one of the slides that we talked about, right? Q and K, right? It's like to shift toward when K and Q are equal to each other because this is at the lowest energy. So this is already at the lowest energy. And this lowest energy, potential energy here, you are having more of the product than the reactant. That's what it means here. Okay, so in this case, it tells us that at this point, right, you see that the product is going to be more stable than the reactant because it produces more of the product, right? It's going to go towards the species that are more stable. So that means the one that is least stable is going to be the reactant. So that means the answer would be A. Okay, so again, the K value will tell you about the stability of the species within the chemical reaction. Okay. All right, 5. Okay, so 5 is giving us the reaction and it also give us the equilibrium constant, okay, at a certain temperature, okay, and it asks us at equilibrium which species predominant, right? So if you think about this, right? So if the reaction is already at equilibrium, okay, you are going to observe both product and reactant. They don't have to have the same concentration, but their concentration have to remain constant. So that means in this case we can eliminate C and D, right? Because for equilibrium you are going to observe both, okay. And which one is going to be predominant? That's when you are going to need to look at the value of K. The value of K come out to be a greater value than 1, right? So 2.8 times 10 to the second. So this is about 200, right? 280. So that means in this case, you have K value a lot greater than 1. What does it mean? Well, when K value a lot greater than 1, it means that at this point, right, you have a lot of product, right, than reactant. So that's therefore you are going to having a big value of K. So that means in this case at equilibrium, right? According to this reaction is product predominant. That's what it tells us. All right, let me summarize this for a second before we move on to the next topic. Okay, so let's take a look at Q and K again. Okay, so Q again is tell us at any point of reaction. Okay, so it can be at any point. It can be at equilibrium when Q equal to K, right? So Q equal to K is already at equilibrium. If Q are not equal to K, it's going to help you to predict whether the reaction would proceed to the left or to the right. Okay, and the reason why the reaction that are not at equilibrium would proceed toward the product or the reactant is because it would like to go toward the lowest energy, which is at equilibrium, right? So we already see that. Now, when you're looking at the equilibrium constant K, the equilibrium constant K tell us that the reaction is already at equilibrium, okay? And because at equilibrium, the concentration remain constant, but they are not necessarily equal to each other. Therefore, in this case, the concentration of each of the species would tell us about stability of the reactant and product. Okay, so we already see that as well. If you observe more of the product at equilibrium, it just means that the product is more stable than the reactant, right? Vice versa. Okay, so that's what we see so far. Okay, the next thing we're going to take a look at is we are going to take a look at the heterogeneous equilibrium. Okay, so we see before in the previous slides, you see that the reaction I give you contain only one physical state of reaction, right? So for example, if it's aqueous, it's aqueous throughout. If it's gas, it's gas throughout, right? So now here, the reaction that I'm going to show you next is going to be a mix of several physical state of the substance. Okay, so let's take a look at A real quick. Okay, so A is going to be an example of homogeneous equilibrium because you are going to deal with everything the same physical state. Okay, so these all are gas. So in order to write out the equilibrium constant expression for this, is still going to be the same as we learned before, right? So it's going to be the concentration of the product over the concentration of the reactant. But don't forget those coefficients. Okay, so raise them to their power. So now the second one, if you think about this, right, this is not homogeneous anymore. This is the example of heterogeneous equilibrium when you deal with more than one phase of matter, right? So you have solid and gas, okay? So when you have solid and gas and other physical state that involve, what you are going to include is going to be only gas, okay? So you are going to treat solid as one, okay? So in this case, because the solid is the product, so I'm going to use one, okay? And then you are going to divide it by the reactant that is gas, right? So we are still including gas, oxygen, and raised to the fifth. Okay, so, and then for the phosphorus solid, that one we will not include. Okay, so again, for the equilibrium constant, okay, so KEQ is equilibrium constant, you are going to include only gas and also aqueous. Okay, the reason for that is because the concentration of the solid and liquid is going to equal to 1. Okay, so you're just going to treat solid and liquid equal to 1. Okay. So now let's take a look at C and D real quick. So let's go ahead. According to this, I want you to write out the equilibrium constant, okay, without my help first. Okay, so once you finish, then resume the video again to check your answer. Now let's take a look at C together. Okay, so C, what does it mean? Okay, so it's going to be only the aqueous and gas, right? So those are the one that we are going to include. Those solid and liquid we will not include. So that means in this case, KC would be just sodium hydroxide squared times concentration of hydrogen gas. Okay. Now what about D? Okay, so D, well, again, we are going to exclude all the solid, right? We are going to include only gas. So that means the Kc would come out to include only carbon dioxide, water, and hydrogen fluoride. All right, so the next thing we're going to take a look at is we are going to take a look at the relationship between Kc and Kp. As I mentioned before, Kc is the equilibrium constant expressed in terms of concentration. Kp is the equilibrium constant as well, but it's expressed in terms of partial pressure. So that means this Kp is going to involve with only gas. And the relationship between Kc and Kp can be expressed according to this equation right here. Okay, so as you see here, Kp would equal to Kc, R is a gas constant, T is the absolute temperature, right? Because it's going to be based off this R constant, Kelvin here. And C, D, A, B, those are going to refer to the coefficient between reactant and product. Okay, so pretty much this exponent right here is going to come from the difference in the coefficient between the product, right, minus the reactant. Okay, so in this case, because Kp is involved with pressure, so that means only the reaction that involved with gas that is going to be able to use this Kp expression. Okay, so it's only gas state. So note that delta N here is the same as what I mentioned before, right? It's pretty much the coefficient of the product, right? And then you minus that with the coefficient of the reactant, right? So that's what that's what the delta N coming from. Okay, so let's take a look at this. Okay, so let's take a look at the relationship between Kc and Kp. Okay, so we are going to write the equation relating Kc and Kp for the following equation. Okay, so let's take a look at A. So if I want to write out the equation relating to Kc and Kp, we're gonna use this equation right here, right? So that means in this case, you will need to know the delta N, which is a difference in the coefficient between product and reactant. So that means you're gonna find out the delta N first. Delta N for A, you are going to use product minus reactant, right? So that means in this case, delta N for A would come out equal to 1, right? Because you add 2 and 1 together, 2, right, from the reactant, therefore you get 1. Now, if you plug the delta N into this equation right here, you are going to get that the Kp can be calculated from the Kc times R times T, right? Now, if you're looking at B, same thing, right? You are going to find out delta N. Delta N for this would come from this coefficient, right? The difference between those. So it's going to be 1 plus 1 minus 1 plus 1. So it's going to equal to 0. So when delta N equal to 0, you are going to see that the Kp would equal to Kc times RT raised to 0. Remember, anything raised to 0 is equal to 1. So that means this is when you are going to observe that Kp equal to Kc. Please note that when delta N equal to 0, you are going to observe that Kp would equal to Kc. So now let's take a look at example 3. Okay, so example 3, now I would like you to actually complete this your own. Okay, so according to what we see some of the example here, I want you to actually start this and then try to work on your own. Okay, so once you finish, then you can check your work with me, okay, to see your understanding. All right, let's check your work together. Okay, so in this case, okay, so we are given Kc. Okay, so we want to know Kp. So I'm going to use the same equation here. So that means we need to find out delta N. Okay, so let's find out delta N. Delta N of this reaction is going to be equal to 1. Okay, so why is that? Why is it 1, Ami? Well, remember Kp, what is P stand for? Is the pressure, right? So which physical state that going to has pressure property? The answer is only gas, right? Because only gas that can hit the valve container, right, exert the force against the valve container. So that means in this case, only gas that is going to include when you calculate for delta N. Okay, so that means the coefficient of the product that involved with the gas state would be just oxygen. So that would be just 1. Okay. So we don't have any gas for the reactant, so it's going to be 0. So therefore, total delta N would equal to 1. So that means in this case, once you plug 1 into the Kp equation, you are going to do next is plug everything in. Kc would be this given value, right? And then multiply by R value, and then multiply by T, right? So remember, temperature have to be in absolute temperature, so you need to convert that into Kelvin first. And after you get this, Kp would come out equal to 0.00042. Remember, the equilibrium constant has no unit. Therefore, in this case, Kp will have no unit. Okay, so it's just going to be without unit. And this problem right here, we know that it's going to be based off this 2 sig figs. So therefore, you are going to get 2 sig figs at the final answer. All right, so this is pretty much what you learn. Like you learn about the reaction quotient Q, you learn about K, you learn about the relationship between KP and KC. Okay, so that's what you learn in this lecture chapter. Please start working on your homework 13.2 as soon as possible.